All right, so in this problem, we're basically going to be covering how you can find the principal stresses, so the max, min, and shear stresses on any structure that we have placed strain gauges on to measure the strain. So we use these strain gauges because they're cheap, they're really easy to use. You can just glue them on basically anything. But the issue is they only measure in one direction. So we need to use multiple of them so that we can essentially come up with a general state of strain in the normal strain in the x and y direction, and then shear strain for the xy plane. So we do that using what's called a strain rosette. So this is our strain rosette. So these are the different strain gauges that we have, and we have given strain values. So this problem is the strain rosette shown is used to measure the strains on a structure of AISI 302 stainless steel. Gauge 1 reads negative 300 times 10 to the negative 6 inches per inch. Gauge 2 reads 200 times 10 to the negative 6 inches per inch. And gauge 3 reads 425 times 10 to the negative 6 inches per inch. So that inch per inch measurement, it's technically unitless, but we use that to identify strain because it's essentially deformation over original length. So it's, um, you know, that's just how we define strain. So we are going to use those values to find the principal stresses, the maximum, minimum stress, and the maximum shear stress. So with these equations that we're going to be using the strain rosette equations, which essentially can set any value of strain on this rosette equal to an equation which is a function of the state of strain that we're looking for. So we can start with the first strain gauge here. So we're going to just label it number 1 just to make it easier. And we know that it's equal to negative 300 times 10 to the negative 6 inches per inch. And so these equations, essentially the idea of them is that it sets it equal to normal strain the x direction times cosine squared of theta, so that is the angle off the x-axis, plus normal strain the y direction sine squared theta, and then the shear strain for the xy plane, cosine theta sine theta, right? So this first one, we can set it equal to normal strain the x direction cosine squared of negative 75 degrees, because it is clockwise from the x-axis, so negative 75, plus the normal strain the y direction, make sure that's looking good, sine squared of negative 75, and then I guess got to put a little down, and then the shear strain for the xy plane of cosine negative 75 sine negative 75. Right, so that's our first equation right here. But we have 3 unknowns, so we need 3 total equations. So we're going to write one for the second strain gauge, which is 200 times 10 to the negative 6 inches per inch. And what we notice here, which is kind of cool, is that this strain gauge is on the x-axis. And the way it's going to work out with all of the angles, that's basically going to mean that whatever value is for the strain gauge is actually going to be our value for normal strain in the x direction. So this is going to be our normal strain in the x direction, and we're going to see how that works out in a second. So e to the x cosine squared of 0, y sine squared 0 plus shear strain for the xy plane cosine 0 sine 0. And then finally for our third equation, we're going to be doing it for the third gauge, and that is 425 times 10 to the negative 6 inches per inch, and that's going to be equal to normal strain in the x direction cosine squared positive 75 degrees, because it's counterclockwise off the x-axis, strain the normal strain the y direction sine squared that's also, yeah, sine squared 75 degrees, also positive, and then shear strain for the xy plane, cosine 75, sine 75. So now we have our three equations. We're looking for our three unknowns, and we just want to solve it, basically. So we're going to start with equation number 2. And basically, here, we're just going to take a look at it. So 10 to the negative 6 inch per inch equals 2. And here, we know that cosine 0 is 1. So that's strain the x direction, normal strain the x direction. And sine 0 is 0, sine 0 is 0. So these are both 0. So boom, we already have a big part of our state of strain right there, normal strain the x direction. So now what we're going to do is we're going to take equation number 1, and we're going to plug that into equation number 1. Right? So 200 times 10 to the negative 6 cosine squared negative 75 plus normal strain in the y direction, sine squared negative 75 plus shear strain for the xy plane, cosine negative 75, sine negative 75. So what we're going to do here is, since there's only two unknowns, we're going to make it so that we can basically set this value equal to a function of this value. So we're just going to basically break it down until eventually we have negative 3.13397. Yes, I know it's a long number. Negative times 10 to the negative 4 is equal to 0.933 normal strain in the y direction minus 0.25 shear strain for the xy plane. So then now we can set our shear strain for the xy plane equal to 0.001256 plus 3.732 normal strain in the y direction. All right, so now we have essentially a value for our shear strain that we can plug into our third equation right here. So 425 times 10 to the negative 6 equals 200 times 10 to the negative 6. Cosine, these are in inches per inch, by the way. I'm just trying to go quickly here. Cosine squared, 75 degrees plus normal strain y direction, sine squared 75 degrees plus and then we're going to plug in our new definition for shear strain. So 0.001256 plus 3.732 normal strain in the y direction. Cosine 75, sine 75. So that, right? A nice and long equation there. But we will be able to simplify it a good amount. So that is going to work its way down to, just to save you some time, 9.8206 times 10 to the negative 5th, which is equal to 1.866 normal strain in the y direction. So then normal strain in the y direction is equal to 5.26 times 10 to the negative 5th inches per inch. Right, so now we have our normal strain in the x direction and our normal strain in the y direction. And to find our shear strain, we basically just need to take this value that we know for our normal strain in the y direction and plug it into that definition that we made for shear strain. So shear strain is equal to 0.001256 plus 3.732 times 5.26 times 10 to the negative 5th inches per inch is equal to 145 times 10 to the negative fifth inches per inch. So that is our shear strain right there. So now we have basically our state of strain that we have been trying to look for, right? So we have our normal strain the x direction, normal strain the y direction, and shear strain. So from this point, there's two paths that we can take. So we started with a strain rosette, and we came to a state of strain. So one method we could do is we could use the strain transformation equations or Moore's circle to find the principal strains, you know, the maximum, the minimum, all that. And then we can use, from there, we can use general Hooke's law in 2D and convert those principal strains to stresses, right? It's essentially just a convergent formula. The method we're going to use is starting with generalized Hooke's law in the 2D to convert our state of strain to a state of stress. So just any known real state of stress, normal stress in the x and y direction, and shear stress. And then we are going to use that and plug it into Moore's circle. We could use the stress transformation equations, but we're going to use Moore's circle. And using Moore's circle, we will be able to find the principal stresses. So now what we are going to do is we're going to use Hooke's law in 2D. So that means that we are going to be looking for some material constants. This includes the modulus of elasticity, so E. And we're looking for it for AISI 302 stainless steel. And so we're just going to look through our little chart in our textbook, make sure it's in US customary units, and we're going to find that it's 28 times 10 to the 6 PSI. So a lot of people will convert this to 28,000 KSI, but I think it's simpler to keep it in PSI, so that's what I do. And then we'll do the same for the modulus of rigidity, which is going to come out to 10.8 times 10 to the 6 PSI, same situation there. And then we're going to look for the Poisson's ratio, which is a ratio that is negative normal strain the y direction over normal strain the x direction, but the method I'm going to use is just using G and E. So it's E over 2G minus 1, which works out to 28 times 10 to the 6 divided by 10.8 times 10 to the 6 times 2 minus 1, which comes out to a Poisson's ratio of 0.2963. So we're going to want to keep these three values in mind here while we use the formula for general Hooke's law. So for our normal stress in the x direction, we set that equal to the modulus of elasticity over 1 minus Poisson's ratio squared times normal strain in the x direction plus Poisson's ratio times normal strain in the y direction, right? So that is 28 times 10 to the 6 PSI over 1 minus 0.2963 squared. Right? Just make sure you can still see that. Yep. And then we will plug in our normal strain in the x direction, which we previously defined as 200 times 10 to the negative 6 inches per inch, plus 0.2963 times, and then our normal strain in the y direction, which we already defined, which is 5.26 times 10 to the negative fifth inches per inch, right? Close those off. There we go. And so this formula right here will work out to the 30.695 times 10 to the 6 times 2.1559 times 10 to the negative 4, which is equal to 6,617.3 psi. We want that in KSI. So our normal stress in the x direction is 6.62 KSI. There we go. Now, normal stress in the y direction is basically the exact same thing, right? E over 1 minus Poisson's ratio, except it's normal strain in the y direction plus Poisson's ratio times normal strain in the x direction, like that. Basically the same thing. So that means that we know that it's going to work out to 30.695 times 10 to the 6th times 5.26 times 10 to the negative 5th plus 0.2963 times 200 times 10 to the negative 6 inches per inch. All right. So now that's going to work out to 3,433.51 psi, which is equal to 3.43 KSI. So that's going to be our sigma y there, normal stress in the y direction. And then for our shear stress on the xy plane, we actually are going to be using our previously known shear strain and G. So it's like that. So that works out to be 145 times 10 to the negative 5th inches per inch times 10.8 times 10 to the 6th psi, which is G, right? And that works out to be 15,660 psi, which turns into 15.66 KSI. So now we have a known state of stress. We have a normal stress in the x direction. We have a normal stress in the y direction, right there. And we have a shear stress for the xy plane, all right? And we did that using General Hooke's law based off of the state of strain that we came up with based off of our strain rosette. So now what we are going to do, as seen here, we've done this, we've gotten this. So now we're going to be using Moore's circle to find the principal stresses, the highest and lowest stresses and shear stress. Now, the point of doing Moore's circle is basically to create an easy to visualize geometric relationship between the two normal stresses and the shear stress. And it is actually a surprisingly easy way to go about doing it, and it is pretty practical. So what you really got to do is you're going to start out with your known state of stress that we came up with. So our normal stress in the x direction, which is 6.62 KSI. You can see that? Yep, okay. That's all right. That was a quick technical difficulty. It's all right. I have a somewhat makeshift stand for my camera, and it just fell. Okay. So, right. Okay, back to where we were. We have our defined state of stress that we just came up with. Right? And essentially what we're going to do is we're going to map out our normal stress in the x direction with our negative shear stress, and our normal stress in the y direction with positive shear stress. Essentially, we're basically representing shear stress on the y-axis and the normal stresses on the x-axis. And we are going to do that because mapping those 2 points out lets us create a circle whose outline essentially represents the relationship between the normal stresses and shear stress, and lets us find the normal stress and shear stress for basically any point on that circle. So first thing we're going to do is we're going to put down, let's say this is 6.62. It doesn't need to be perfect. And we'll say that that is 3.43, right? So we're going to move up to, we'll call that 15.66. And so bring that down to about, I know there, for negative 15.66. And so we're going to map out, this is our sigma x comma negative tau xy. And here is our sigma y comma tau xy right here. So these 2 points right here are points on this circle that represents the relationship, right? That allows us to find basically any normal or shear stress. So what do we do from here? Well, we want to connect these 2 points and find the center of this circle, which will be the average between these 2 stresses here. So we're going to look for sigma average, the average stress, and that's equal to sigma x and sigma y divided by 2. And that's going to give you 5.025 KSI. So 5.025 is our center point right here. All right. So now what we want to do is we want to find the radius of this circle, because if we have the center point and we have the radius, we will be able to find all of the endpoints, you know, the max values of this circle, basically. We'll be able to know how far along the x-axis it might be, or how high or low on the y-axis it might be. So what we do is we're going to use the Pythagorean theorem and basically create a little, right triangle within the Mohr circle here. And this little right triangle is going to allow us to find what r is right here. So basically this side of the triangle is the difference between these 2 points, and this side of the triangle is tau. So r is equal to the square root of 6.62 minus 5.025 squared plus 15.66. We don't need to worry about units because it's squared, like that. And then that becomes 15.71 KSI. Now, because our circle lies on the x-axis with the center on the x-axis, and y is basically representing shear stress, the highest y value is basically just going to be the value of r, right? Because that's how high up off the x-axis it's rising. So this value right here is actually our maximum shear stress, because maximum shear stress, as you can see by the circle that lies with its center on the x-axis, is always going to be in that vertical plane. Now, we're going to be looking for our principal stresses, which are the maximum and minimum stresses, and those can be found by looking for the maximum and minimum x values on this circle right here. So we're going to create a very, very crappy circle, but we don't need it to be perfect because it's more of a visual thing than really a necessity. So we'll have that be our sigma 1 and that be our sigma 2. And these are really easy to find. So sigma 1, we will be finding that just by adding our radius to our center point. So 5.025 KSI plus 15.71 KSI. So our sigma 1 is equal to 20.76 KSI, right? So that, right, is going to be this value right here. See that? 20.76. And that's going to be the highest normal stress that this structure experiences. This is the highest shear stress that this structure experiences. And then we'll be looking for the lowest by subtracting our radius from our center point. Negative 10.72 KSI. Boom. So that's our sigma 2. Right, so negative 10.72. Right, so essentially what we just did was we took our strain rosette using 3 strain gauges measuring the strain on a structure. But because they all measured in one specific direction, we used the strain rosette equation to create a system of 3 equations to solve for our 3 unknowns to create a defined state of strain. So a normal strain in the x direction, a normal strain in the y direction, and a shear strain for the xy plane. So using that system of equations, we defined those 3 values, and that allowed us to go into Hooke's law in the in 2 dimensions and figure out what the state of stress was based off that state of strain. So then we got a normal stress in the x direction, a normal stress in the y direction, and then a shear stress for the xy plane. And we did all of that using these equations here and these material constants to give us some values. Then, with that state of stress that we knew, we were able to use Moore's circle to essentially create a visual geometric relationship between the shear stress and the normal stresses on this structure. Any point on this circle represents basically a possible value depending on what's going on, right? And this stress right here, sigma 1, that's the max normal stress that this structure will experience, 20.76 KSI. Sigma 2, that is the minimum stress that this structure will experience. That is negative 10.72 KSI. And tau max right here, that is the max shear stress that this will ever experience. That is 15.71 KSI. The minimum would be negative 15.1 KSI, which would be down here. But right here is tau max. So that is max, and that is minimum. So I hope that was pretty clear and easy to understand and helpful. And thank you for listening.